our next speaker, we have Dr. Carle Pieters. Dr. Pieters is a lunar research professor in geological science at Brown University and the principal investigator for NASA's Moon Mineral Mapper experiment. Dr. Pieters is going to talk to us today about the moon's properties and its geology. Dr. Pieters.
Okay, well, this is a formidable task to squeeze into a couple of minutes, so at least I hope I can give you a taste. If we could go on to the next slide. These are the general topics that I'd like to spend time on. The first half, I'll really talk about, in a very condensed form, some of the geology implications of the lunar evolution, just the basics. Some of this has been mentioned by both Jack and David, about impacts and craters, and of course the regolith. And following me will be a discussion of the dust, so we'll learn about more of that later. Then the second half, if I still have time, I'd like to talk about some special areas that are different from most of the things that we've studied thus far with Apollo, but clearly are going to be important in the future. Next. First of all, the image you're looking at is an image obtained by Galileo as it left the Earth-Moon system on its way to Jupiter. And the moon that you see there, of course, you're looking at the far side of the moon. So let's go to the next slide. The far side of the moon has similarities to the near side, of course, but you can see very clearly a lot of its history clearly demonstrated. There are dark areas, there are bright areas, there's clearly impact craters. Next slide. And the moon, if you look at topography, is covered by impact craters. It's exposed for more than 4 billion years, and it retains the evidence of that interaction. South Pole Aitken Basin is the largest documented basin on the moon, and as you can see, covers an extensive area on the far side of the moon. Next. Okay, looking at the near side and far side together. The near side, of course, is what you're familiar with when you look at the moon any night, and you see the dark areas that form a man in the moon, or a lady, a rabbit, what have you. And those are the basaltic terrains that are very similar in basic properties to basalts on the Earth, but were derived from the interior, as Jack mentioned. The bright areas, however, is the original crust of the moon. It's older than the basalts. The basalts came a couple 100 million years later, and it documents the primary crust that formed on the moon prior to the rest of its geologic evolution. The low albedo of the basaltic terrain is because it has a lot of iron and magnesium-rich minerals in it, whereas for the brighter highland crust, the feldspathic crust, has a lot of calcium and aluminum minerals, and that makes them brighter. Now, the brightest part you can see is associated with some of these craters. That's because these craters with these raised systems are younger than the rest of the terrain. Gradually, with time, those will be subdued with the weathering of the surface in the lunar environment. Next slide. Okay, here's an overview of lunar geologic history in one slide. Let me walk through a few of the items that have been mentioned. Along it's a timeline, essentially, from the beginning to where we are now on the right. The dashed line at the top separates two principal eras, the pre-Nectaran and everything after it. And if you look at the bottom, it's an entirely different time scale. The first 500 million years of lunar history had a lot happening. It had this melting of the outer surface by whatever reason, that gradually crystallized, forming the primordial feldspathic crust, rich with the aluminum and calcium minerals, and the mantle, which is lower and contains many of the iron and magnesium-rich minerals. As the crust formed and became solid, with time, the mantle itself, with radiogenic decay, heated up, and you had an extrusion of basaltic material. That's sort of the dividing line at about 3.8 billion years, where basaltic volcanism began on the surface of the moon and spread across both the near side and less so on the far side with basaltic materials. So the basalts are smoother, they are younger by a couple 100 million years, but nevertheless have regolith that has been formed on them. Next slide. Now, as was mentioned, on the moon, there's no rain, there's no atmosphere, there's no wind. Next. The only thing that the moon does have a lot of are impacts, a continual rain. Fortunately, the size of the impactor has decreased, and we have infrequent larger ones, but very frequent small micrometeorite impacts. But of course, we have radiation, both solar radiation and galactic radiation, because there is no atmosphere. And these two proponents make the moon's surface what it is that we see today. Next. The moon is covered with fine-grained regolith. As you've seen from the previous talks, there are rocks, there are boulders larger than Jack, but essentially the regolith is everywhere, not only in boot prints, but you can see the tracks across the surface made within the regolith and is preserved today with the current sensors. Next. Now, as I've alluded, there is weathering on the surface. How do you go from rocks to these intricate regolith components that David discussed? Well, summarized here is all the various processes that are complex, they act at different times, but because the moon has been exposed for such an extended period of time, it accumulates and has a uniform, well, relatively uniform sequence, both on the mare as well as the highland surfaces. Essentially, there's space weathering everywhere, but because of latitudinal differences, radiation differences, you do have some variation in the ultimate accumulation. Next. Now, my specialty is spectroscopy, looking at how light reflects from the surface, and I look at it as a function of wavelength. And I have two examples here of samples measured in the laboratory from the visible part of the spectrum to the longer wavelengths and how bright they are. And this shows you the principal effect of this weathering process, say for the Apollo 17 samples. Shown here is a basaltic sample in blue. It has these two beautiful absorption features that are due to the mineral pyroxene within the rocks, but it has no weathering. Similarly, a mature soil from the basaltic terrain has much lower albedo in the visible, and these absorptions are very subdued because of the weathering products. If we look at the surface with remotely, such as the M-Cube instrument, we see the same effects. So we know that the samples have documented the kind of effects that we see throughout the surface of the moon. Weathered products have weaker diagnostic absorption bands. They become darker across the visible, and they develop this overall slope to the continuum to longer wavelengths. Quite consistent everywhere we've looked thus far. Next. Sorry, I was supposed to show this when I talked about pyroxenes. Okay, those are the pyroxene bands. Next. And there's the visible wavelengths. Next. Okay, now with more than 4 billion years of history, the moon's surface holds many secrets, not just mare highlands, which we have sampled during the Apollo, and we've studied them through the Apollo samples for the last 50 years. But there are many things we don't know, and I'm going to highlight a few in the next slide. These are things that we haven't sampled. The next talk by Kevin Cannon will talk about the character of the poles. The poles we've looked at remotely. We know there's hydrogen there. We suspect this is linked to ices. We know it's cold. It's very cold. I'm going to spend a little time, whatever time I have remaining, talking about swirls, Reiner gamma, and I'll tell you what that's about, but they're unusual albedo features that are neither craters or mixtures of unusual compositions. Then there's the irregular Mare patches shown over on the right. These are small features, no more than a kilometer or two in scale. They occur in volcanic terrain, and they clearly have a different texture that we've seen anywhere. And whether it's because they're very young or they're very old and are the last gasp of volcanism, we have no way of telling until we go there. And lastly, and this I can't speak of, we know from the remote measurements there's a diversity of rock types across the moon that have not yet been sampled and will tell us a lot more, will fill in some of the holes that we have in our current understanding. Okay, in the remaining few minutes, let me tell you a little bit about swirls. Reiner gamma, which is shown with the blue arrow there, is going to be a NASA CLIPS landing site planned in the next couple of years. It's a prominent magnetic anomaly in Oceanus Procularum on the near side. Now, there is no current magnetism on the moon. There was a dynamo, and then with the remote measurements, we've identified these areas that have magnetic anomalies that are very localized, constantly called magnetic anomalies. Next slide. Reiner gamma, this is what it looks like under high sun where there's no shadows. Next slide. This is the same feature with a low sun, and you can start seeing some local topography. There's this group of cinder cones, essentially, small volcanic terrain to the north. You can see the craters. There's some wrinkle ridges. You can't really see anything at the albedo feature itself. Next. If you look at block populations from the diviner, there's no signature. There's nothing to do with blocks there. Next. Topography, yeah, you can't see Reiner gamma. There is no topographic relief that can be identified. Next. Stepping back from that, topography on the left, albedo on the right, you can see the craters. Over on the right is the beginning of some highland terrain. So Reiner gamma occurs right in the middle of this vast volcanic plains and is this highly unusual albedo feature. Next slide. Okay, well, what is it? It's not because it's a different composition. We've tested that with several different of our remote sensing approaches. It's not freshly exposed material, and I'll show you some evidence for that. So it's neither of the primary reasons that cause albedo differences on the moon. It has no relationship to topography, but it does have a magnetic anomaly. It's associated with a mini magnetosphere associated with this particular feature. And you can see these beautiful wispy character of the feature. Next. Next, okay. Let's skip over this. Next. Next. We'll look at one traverse from MQ through across the swirl, and this is the 40-kilometer swath width. And I can show you 4 different traverses. First, we'll look at some in the lower part of the image where it's general basaltic terrain, and then we'll compare that to the terrain that we see in the swirl itself. Next. Next. Okay, here we have a zero in on these 2 craters down in the south, which are typical basaltic terrain. And if you remember what things looked like when I showed you the Apollo 17 soil and crater, what we're seeing down here as we do a traverse across a crater, you go from a soil into a crater, which is the blue, and then back into the soil. The same thing is when we have the larger crater, which is older, but has developed material on the surface of the soil. You can start with the background soil, you go down a steep slope, which is freshly exposed material onto the floor, then back onto the local soil. So it's comparable to what we've seen in the laboratory with freshly exposed basalt compared to the well-developed regolith. Next. Also, there's this continuum slope difference, which I won't talk about much. Next. Okay, soils are brighter at all wavelengths when we look at a traverse across soil, shown on the left there. If you go from the swirl to the dark zone, back to the swirl, you see the soil looks the same as what we saw elsewhere, but the character of the swirl itself is basically a brightening at all wavelengths, not just the visible. We believe this overall slope, red slope to the swirl material is due to the nanophase iron that was mentioned earlier. It's a weathering product, but the character of why it is brighter than the surrounding soil is something that we haven't looked at extensively, but are looking at more recently, is if you go to the larger scale developed metallic iron, the micron size, which you can barely see, that those particles have no spectral effect except darkening. So the hypothesis is that these areas have the uppermost surface weathering product, but they don't have the developed micron size weathering products within the soil. Next. And I think what I'm going to have to do is just, let's go next, please. I'll move ahead quickly just to get to the last slide so we can, next. This one is comparing the swirl to the fresh craters, and we want to know, are these properties comparable for everywhere else? Next. And what we'll look at is images of the visible and images right in the middle of that pyroxene absorption. And you can still see the beautiful swirl, but what you see is also that the weathering product, namely the strength of the pyroxene absorption, now is affecting the character of the measured spectrum, and all the fresh craters are little black spots, which is what we saw in the spectrum itself. Okay, let's move forward. I think I'll go to the end and tell you what a few of the ideas we think about what, okay, hold it here. One last thing is that these swirls, and this is the only time I'm going to mention water, David, I'm afraid. The swirls, especially in the mare, are probably the driest areas on the moon. On the right is a measurement, an estimation of the very weak absorption due to OH at the longer wavelengths, and it essentially mirrors the character of the swirl itself. Next slide. Okay, what are these? Next. They're well-developed soils that have these nanophase ions on the grain, but there's two hypotheses of how they happen, which hopefully we'll be able to tell once we land and look at this. One is that it's produced by a fairy castle structure, and David briefly mentioned a fairy castle structure. The solar wind charged particles have electrostatic interactions with the soils, which create a very, very porous structure. If you remove the electrostatic, the charged particles, and compress that or collapse that, the soil becomes brighter. It doesn't have the dark structures that it can capture. The second hypothesis, and let's move to the next slide. There we go. The second is that the reason that they're bright is that they don't have these micron size iron particles. Well, how can you get rid of them? Well, one is that because they're in this magnetically shielded area, that the development of these larger size iron particles require reduction by solar wind hydrogen. If you cut off the solar wind hydrogen, you don't produce the micron-sized iron. The second related hypothesis, though, is that, well, space weathering proceeded as normal. You produced everything, the micron size, the nanophase size, but because it's in a magnetic field and you do have gardening, every time a particle would be boosted up, it would be caught in the magnetic field and moved over. And gradually, over millions and millions of years, you'd remove these particles that have the micron-sized particle, these grains that have the micron-sized particles out. We don't know the answer to this. I leave this with you to show you that we don't know everything yet, but there are a lot of very physical properties of the surface of the moon that we really are eager to learn more of and hopefully will in the next few years. Next slide. So stay tuned. Thanks.
Wow, thank you so much for that talk, Carly. And you've left us with a lot of future ideas and that we need to be thinking about to undertake and explore on the surface of the moon.